Hi, today's lecture is about blockchain based smart contracts. It is actually a deep dive into smart contracts. You had a brief introduction to the Ethereum platform last week, but today we will do a deep dive into the smart contracts platform. Today's lecture is mostly based out of a tutorial that we developed by called the Introduction to Smart Contracts, co-authored by me, Dr. Sheth, and Dr. Lee. So we will look at what are smart contracts, what are the examples of smart contracts. We look at the various stages in Ethereum smart contracts, the various stages of hyperledger smart contracts, and overall look at different applications of smart contracts and issues with smart contracts in this lecture. Start with smart contracts and this premise of contracts. Hart and Holmstrom were two professors at MIT and they won the Nobel Prize in Economics in 2017. Their main idea was to model firms and businesses as incomplete contracts, with contracts being written with the sole aim of smoothing frictions in transactions. So now let's deep dive into what incomplete contracts are. So why do we need firms to exist per se? Why do we have employees working for firms? Why do we have firms interacting with other firms, so on and so forth? So the idea is whenever a firm is set up, they really know what their products are, but it's never certain that this is the exact nature of the work you're doing. Let's say, for example, you join the Toyota Motor Company, which is developing the Corolla car. Over a period of time, you develop Corolla V1, Corolla V2, and today we have Corolla version 18. So, how do employees join the firm for a pay? They are told as part of the contract that you will be reporting to so and these will be the general ideas of your tasks, or these are the kinds of jobs you would do. But once you get into the company, then then the managers would want you to work on, say, design or specification or something that makes their product sellable, right? All of these specifications are not known to the company at the time that they actually sign the contract or issue the contract to you hiring. Okay, so these scholars, they argued that contracts reduce frictions in transactions that result from uncertain transaction costs. They reduce irrational behaviors of actors. Like, for example, you know that you're reporting to somebody within the company. Doesn't mean that once you get a job, you start working on your own, right? It also discusses incentive incompatibility. For example, you exactly know what your pays are, what your bonuses are at the end of the year, so on and so forth. It discusses cognitive limitations. Like, for example, what do you think are the bounds of a person's thinking, right? And how long can a person think on a certain line? And then other factors that are detrimental to businesses happening smoothly. So further, Hard and Armstrong later, right, in 1986, they contend that the economic credibility of this contractual approach to organizations can often become complex because contracts themselves are incomplete. The work is really not known, and in addition to being incomplete, it's also very difficult to enforce. Like, for example, if somebody breaks the contract in a company of like 360,000 people, if one guy decides to not show up for work or decides to disappear one day or join another company the same another day, what would this company be able to do? Would this company be go after this person? Would this company sue this person? How does it work, right? And for example, if the person has gone to another country, then can this company pursue the person in the other country? What are the jurisdictional boundaries, so on and so forth? Okay, so let's take an example of the insurance sector. A customer who purchases an insurance policy which is mandated by law often encounters problems of enforcement when she must submit a claim. Like, you could have many different insurance validators, you could have insurance agents, then the law enforcement agency that basically certifies that this car is damaged, and many different mediators between the customer and the insurance firm, each of whom expect a cut in the transaction, right? And all of these make these transactions inefficient. In addition, insurers also have different incentives than the insured people with regards to payments of claims. Such incentives mismatches can be generalized for each intermediary involved in such a transaction whenever contracts are written between the insurance company and the individual that's being insured. Continuing this example, let's put some numbers to it. Say you have this flight insurance and your claim of insurance is $500, right? The flight got delayed, didn't take off, so you want to claim $500 as the damage for this flight. So let's say the insurance company here or the person that promised you this $500 for the flight insurance doesn't want to pay you. Then the cost of you needing to go to through the legal process and then suing them through the small business courts, etc., is much higher than just the $500 that you're supposed to get, right? So you normally let it go. That's why these markets where insurance exists are very hard to basically fight and gain an advantage of. Not to mention this asymmetric information, legal and market power of large insurance companies versus a lone individual customer. Let's say you go to the court and you basically sue the company saying, okay, this guy didn't pay me $500 for this flight. Now the insurance company, they have all this wherewithal, they have teams of lawyers, so on and so forth. They basically send their entire team and basically send them to you, and then you better basically uh, either set up a legal team that is equally forceful, or you let go the $500. So such difficulties due to differences in this market power, access to legal resources, and domain knowledge with the parties involved in a contract often increase frictions in markets, thereby reducing the demand from customers who are wary of the hassles of such claims. With smart contracts, examples on Ethereum, the insurance policy itself is configurable since templates are readily available and risk models associated with each template is already known to the insurance firm. Let's take an example. In the case of a flight delay insurance, a blockchain can validate an event of interest, that is a delayed flight from flight monitoring systems, and process insured customer claims automatically. As an example, an insurance firm can operate as a platform that creates a smart contract infrastructure on top of the blockchain system, thereby integrating with different external systems, like, for example, the flight database, the weather database, the national know your customer, anti money laundering registries, etc. Okay, so we say that whenever you automate these kinds of contracts where payouts are automatic, it's possible that you don't need to basically file a separate claim with the insurance company and then go through the entire process. The moment there's a detection of a delayed flight, you get the $500 automatically because it's all enforced on as a smart contract and it runs always on a blockchain. Okay, so here in this case, independent developers, resellers, insurance agencies, or crowdsourcing platforms can create and encode different unique risk models which operate using smart contract infrastructure. So insurance agents such as travel sites, etc., and resellers can customize insurance policies to suit different customer pools. This is a shift from a one size fits all model used in traditional flight insurance marketplace. For example, one could charge different insurance premiums for the flight delay insurance product based on the time of delay. For example, if you can pay $10 and get the insurance for a 30-minute delay. Similarly, you could pay like and then the insurance could be premium could be brought down to $10 if you basically expect the flight to be delayed by only half an hour, and the firm that insures you pays you about 25% of the ticket fee. Similarly, if the flight is delayed by more than 1 hour, you could pay like a $20 premium for the flight insurance, and the customer could get about 40% of the ticket fare in case of a 1 hour delay, and so on. You could configure it, say, if it's delayed by more than 6 hours, you get the entire flight ticket reimbursement back for a premium of $50 and things like that. Okay, so with smart contracts, the time needed to effect this change of configuration of these parameters, which is the time taken to the time delay and also the amount of money that you pay a customer, this can greatly be shortened because all of these components are written in software and are pretty much rule based. The software automation of these smart contracts makes these possible, these micro changes possible at a higher rate of efficiency. So insurance companies, resellers, etc., can directly configure certain parameters in the insurance policy and get these out to customers to buy and use. So this is how we can say that there are different life stages in the life cycle of a smart contract. First stage is you define what the contract's rules are. These are the rules of interface between, say, an insurance company and the person who is insured and the customer. Okay, and then this contract is defined and it's written and executed. Now, this contract sources information from what are known as oracles. These oracles could be outside the blockchain system. They could be like, say, weather monitoring systems, or like, say, flight databases which give you real-time information about the flights that are about to take off, so on and so forth. So once an event is triggered, let's say there's a flight delay from Miami to New York, and the flight database tells you, okay, this flight is delayed, then you immediately get this information saying the flight is delayed, and it executes a certain set of conditions. So like, for example, in this case, so say you are to basically pay the insured person the entire amount of the flight because it's delayed by 2 hours or 3 hours or something like that. So the smart contract will execute and transfer this value to the end user. Next is the question of settlement. So once this monies are transferred, then the person end user has to understand that he has to check or validate with the banking agency or whoever or whatever else that's out there that the monies have actually been received, and the insured company or the travel agent that is responsible for this flight also knows that this amount of money has been debited from his account uh, because somebody has to pay the insured person. It's not all coming out from the insurance company, right? And then the settlement could be of two types. It could be on chain or it could be off chain. Like, for example, if there's a cash transfer that's involved, then it could mean converting the cryptocurrencies or the tokens into US dollar equivalent and then depositing it into the insured person's bank account. So these are off-chain transactions which happen off the chain. However, if the end user or the customer has agreed to receive the amount in Ethereum or Ether, this trans settlement could happen directly on chain, wherein the money is moved on chain. So we observe this life cycle and how the contract progresses from the setup stage to the stage of dormancy, like once it's deployed onto the blockchain, and later, when the logical conditions and the smart contract are met, uh, it is triggered and this stuff is executed on the blockchain. On the overall, contracts through automation and operating as a software program with a life cycle with definite times of completion and steps that are encoded in the programmatic logic can definitely make business processes simpler. Here's another example. Let's say the term which basically puts it in terms of a flowchart. So initially at step one, you have different terms and conditions of execution of the contract that are agreed upon by all counterparties. All information is stored transparently on the blockchain or on oracles which are external to the blockchain, and this is basically executed and runs on the blockchain network as a smart contract. Okay, once all of this information runs as a smart contract on the blockchain network, it would be executed when the conditions have been met. If the conditions have been met, it triggers this execution on the blockchain and the smart contract is executed on the network. If the conditions are not met, like for example, if there's no flight delay, it doesn't do anything at all. Okay, so that is how the logic flows. So how did these smart contracts come about, right? So Nick Szabo, one of the scholars, he's considered to be a genius polymath. He has a couple of doctorate degrees from various universities in the world, and he works at the intersection of technology, law, science, and economics. Okay, so he's a polymath, and he's widely recognized by scholars to have formally defined what the smart contract is, And he defined smart contracts as a secure, machine readable, and executable program that can automate specific procedures, including those used in legal contexts. Okay, that's very important to note. You must have heard this example of a vending machine from the last class, if you remember that. That was a crude way of discussing it, but he specifically defined it very precisely. Okay, so the basic premise behind smart contracts is that different types of contractual clauses, for example, rules pertaining to insurance settlements, collateral bonding, property rights, can all be embedded in computer programs using cryptographic validation mechanisms to breach uh, to make this breach of contracts very expensive. Okay, so functionally, he described them to be metaphorical equivalents of vending machines in terms of transactional efficiency and automation. So he says that vending machine, the primitive ancestor of smart contracts, uh, because the vending machine is a contract with a bearer. Like anybody with coins can participate in an exchange with a vendor. It's very difficult to break, so on and so forth. Again, bringing into your attention, this is lockbox and other security mechanisms in within the vending machine, which makes it very difficult uh, to attack. Right? For example, if you have to steal a coin or if you have to steal a lockbox, you have to break open the entire vending machine, so on and so forth. The penalties are higher for breaking it than for actually just paying $1 and getting the coke out of it. Right? So, most recent research has defined smart contracts as the self executing financial instruments that synchronize their state, often through the blockchain. So, when running on a blockchain, smart contracts becomes something like a self operating computer program that automatically executes when specific logical conditions are met. So, it is smart because it contains programmable logic which can take many different forms and can automatically execute the terms of the contract without intermediation. So Mick is another scholar. He argues that smart contracts can have legal validity and are enforceable, similar to traditional contracts. So in particular, business and financial contexts. Nevertheless, other scholars or other industry people note that different complexities in enforcing smart contracts by means of consensus, either simple majority or absolute majority mechanisms, on the blockchain are much more different than legal enforcement, because here you don't basically follow the rule book, but you tend to vote, or you basically say yes or no, and you basically have this consensus mechanism where 51% of the network is enough. But is the 51% good enough to decide the law? Need not necessarily be, right? So, so fundamentally, whenever smart contracts um, have to basically come into play, what happens when there are hard forks? So, whenever a blockchain splits into two, um, here you cannot say that the code is a law, because now you have two different versions, and both different versions cannot be the law simultaneously. So some legal jurisdictions have started to establish legal structures to facilitate, validate, and regulate all the encoded software uh, in the context of businesses. So imagine this is very challenging, right? So in the terms of a contract, you have, let's say you're buying a house or something, you have the seller, the buyer, the dealers, and a bunch of intermediaries like the notaries, so on and so forth, who sign off on these documents, right? Now you're saying that you not only have all these people participating on the network, but all of them are participating using their computers on blockchains, which basically interact with software, and there's no physical person reading through the laws, etc. It's all understood, and then you just sign off using a private and public key. So this makes it a lot more complex. And now what happens if the system breaks, or if there's a fundamental software flaw? Who is answerable? Okay, so these are very big challenges for smart contracts. So because smart contracts run on the blockchain and are created using fourth generation programming languages like Solidity, they run exactly as programmed without any possibility of censorship or downtime, fraud, or third party interference. Smart contracts execute on a variety of blockchain networks. So while Bitcoin blockchain provides only limited support for smart contracts, most of the later platforms such as Hyperledger, Ethereum, EOS, Corda, etc. I have a list of about 40 of them with me. They've all made allowances for writing a separate business logic programming layer. Okay, information system scholars have started analyzing smart contracts as a tool for business process reengineering due to several features that smart contracts contribute to existing business process. So most features listed in this table pertain to smart contracts per se, but some are accomplished because of the features of the underlying blockchain. So let's look at this small table in the next page. The different features of smart contract like reusability, automated verification, programmability, version management, formal verification, business process reengineering, and different types of smart contracts like Ethereum, Waves, Corda, Hyperledger, Lightning Network, so on and so forth support several of these features. Some of these features are directly inherited from the blockchain. Like for example, decentralized execution, immutability of transactions, transparency of transactions, security of transactions, etc., are directly derived from the blockchains. But smart contracts themselves provide a set of features that are useful to smart contract creators. Smart contracts, through templatization, repetition, and through mechanisms that facilitate historical and public records about risks of execution, alleviate some of these uncertainties in transactions, thereby enabling faster times to create and settle contracts. There are different steps to write smart contracts, which we will go through now. Okay, the first step is writing smart contracts and distributed applications. Distributed applications implement smart contract programs and provide user interfaces for executing smart contracts. Authors of a distributed application or the initiating party in a transaction sets the rules for the contract. These smart contract programs adhere to common standards such as ERC20, ERC720, ERC50, which define application programming interfaces to the Ethereum virtual machine using the Solidity programming language. Very often, smart contract programs are developed incrementally and inherit previously developed smart contract templates from public repositories such as GitHub. So in the next step, basically you test the DApp. Once the distributed app or decentralized app is written, these will interact over remote procedure calls with other DApps on the Ethereum network or directly with the Ethereum virtual machine. So DApps can be commissioned using the Truffle framework and the Truffle console, which provides a Web 3.0 instance of the Ethereum virtual machine to test the DApp code. Further, DApps can also be deployed on Ganache, a one-click blockchain to mimic the Ethereum blockchain functionality on a single standalone desktop environment. Okay. There are also libraries available like Web3.js to build client-side applications with JavaScript framework like React, Vue, or AngularJS, and the associated test suites which can actually be used to test these decentralized applications. So I've given the link for Truffle and Ganache if any of you are interested in looking at creating smart contracts using Ethereum. So the next step is basically to deploy the smart app developed and tested using remote procedure calls, etc., on your desktop environment to the blockchain. You can't directly go and launch it on the Ethereum blockchain and see things break because once you put it on the blockchain, every transaction has a fee, right? Has a gas fee or ether is spent to basically transact on the network. So instead of directly launching it on the Ethereum virtual network, you launch it on the test network, or testnet. So once a contract is written and tested on a standalone environment, it is deployed onto either Ropsten, Koan, or Rinkaby test networks. There are about five to seven different test networks. So what these test networks do is they emulate the Ethereum blockchain network, and they allow different types of decentralized app writers to come and write their contracts and test them out in a simulation. We will do one of these with the Koan or Rinkaby test network next week during the online class, where we will actually create our own smart contract and basically launch it on the Rinkaby test network and basically see how this contract interfaces with the Ethereum virtual network. Okay, so dummy ether, which is a crypto token used to fuel transactions on the blockchain and to pay the transaction fees, is obtained from what is known as network faucets. And the network-based systems tests are performed to test all of these smart contract functionality. Okay, so once these DApps are deployed on the main network, then the next step is to actually deploy it on the live network. So this is known as the mainnet deployment. Once tests are successfully run, the contract is deployed on the Ethereum blockchain's main network. Each contract creates a new account with a unique identifier which is stored in the world state of the blockchain. This then creates a unique contract storage wherein smart contracts bytecode gets stored and referenced. So the blocks contain the root hashes, the top of the Merkle tree data structure, used to store the set of transactions. A root hash is used to validate the integrity of these transactions. Uh, and the current state, the transactions in the block, and the transaction receipts are the different fields that are stored on the network. The last stage of a transaction, after launching this DApp on the mainnet, is to basically enforce this transaction. So each type of transaction on this network have, like for example, if you're sending data, if you're receiving data, if you're storing variables, if you're validating logic, spends a certain amount of Ethereum, and this Ethereum is known as gas. Okay, so these gas payments are credited to miners in the network for spending computational power to validate these transactions. For example, each time a contract invokes a function to send the data using the sendTX function, it costs a fixed amount of gas. So this gas fee increases by the set of bytecode and the constructor functions being executed. Meanwhile, the gas fee varies by the number of transactions in the network, whether miners are able to select the corresponding transactions at the offered fee. A user can pay gas for other transactions as well. For example, for using data stored outside, gas payments can avoid these spams, and gas limits can prevent the Turing halting program wherein blocks are overfilled with too many transactions such that further transaction processing on the network becomes impossible. Okay. So now let's look at Hyperledger Fabric. Hyperledger is an initiative of the Linux Foundation. It started in 2015 with several member companies like IBM, Intel, JP Morgan in a consortium. So it is an umbrella project of open source blockchain technologies and related tools to support collaborative development of blockchain-based distributed ledgers. A Hyperledger blockchain system consists of key component parties, channels, data objects and their states, transactions, ledger endorsement policies, smart contracts, and ordering services. A party can be represented as one or more different nodes called peers. Transactions performed by any partner in order of payment are stored in the chronological sequence of successive blocks in the ledger kept at every peer. So a subset of parties can set up a channel to conduct business among themselves so that their ledger can be segregated from others for the purpose of transaction privacy and confidentiality. Channels also greatly increase the efficiency, such as since a transaction only involves the parties within a channel, and party can conduct transactions through multiple channels simultaneously. Within a channel, parties share a set of data objects in exactly the same states as that of a ledger. By terminology of Hyperledger, a data object is called an asset, and states of all assets make up a world state to reflect the values of actual data objects in the real world. Asset states are stored as attribute value pairs in a database. While the world state provides the current states of the assets, the ledger stores all the history of assets from their creation to the world state. So in the following slide, what we see here is a simple Hyperledger contract written in the Go programming language by Google. Okay, so here we try to use the same example as that of a flight delay. So we describe the customer ID and the flight first, and then we set the policy uh, for the flight delay. Like for example, if the flight is delayed by so much, pay the user so much, and then you basically execute the logic or write the code for the logic to validate the flight delay insurance policy details. For example, whether the policy exists, whether it does not expire, and then how much time should the customer claim it, so on and so forth. And then once the customer submits a claim online on the Hyperledger platform, So you basically validate uh, the particular flight ID and the flight departure date, and process the reimbursement or the claim onto the ledger based on the amount of time it takes for the flight, or based on the policy details. So next we discuss how the smart contract is invoked to create a transaction. The five steps are proposal, endorsement, assembly, ordering, and commuting. Okay, so these five steps are conducted in order for a transaction to actually be committed onto a blockchain using the hyperledger framework. Now let's look at what each of these do. Okay, so the first stage, which is proposal, here a peer acting on behalf of the party can invoke the smart contract deployed locally to make a proposal and submit the proposal for endorsement. So in the flight delay example, any involved party, example a customer, can execute a smart contract which is shown, uh, and make a proposal with the execution result including the data objects read and written, and send the proposal to the airline and the insurer for the endorsement. At the endorsement stage, each receiving peer independently executes a corresponding smart contract uh, which has been installed locally and determines the data objects to be read and written by the contract. If these read and write set values match the values that the peers have received in the proposal, they sign the response as proof of endorsement and return it to the proposal peer. This is called validation by simulation. In this example, the insurer and the airline both execute the smart contract shown in Appendix A locally, check if they reach the same result as shown in the proposal, and then send their endorsement response back. In the assembly stage, once the proposal peer, that example, the customer receives all the required endorsement response, it checks the results from each response and determines whether the transaction was properly endorsed. If so, it collects all the endorsement responses as an uncommitted provisional transaction and forwards it to an orderer in the ordering service of the blockchain system. In the ordering setup stage, the orderer collects the transactions from the peers, sorts them by channel and transaction timestamp, assembles them into blocks, and finally delivers a message containing the newly created block to all peers in the channel for committing. In this case, the orderer sends the blocks to peers representing the customer, the insurer, the airline, so that they can commit the transactions. The last stage is known as committing. To prevent double spending, each peer validates every transaction and received block again. Specifically, each peer checks if the versions of the data objects in the transaction match the current version of its local data objects. If a block is valid, it adds the block to its ledger and notifies the proposal peer, example the customer, that the transaction was committed successfully. Otherwise, a failure notification is sent. So we compare Ethereum with Hyperledger in the tutorial, an introduction to smart contracts, concepts, technologies, and applications. Here we compare the four different parts, which is workflow, security control, consensus, and scalability of Ethereum and Hyperledger. So with Ethereum, the smart contracts support event-based execution of contracts in the workflow. So for example, for any stage to any stage, you have to have an event trigger. Whereas in Hyperledger, the workflow clearly contains the proposal, endorsement, assembly, ordering, and committing steps with different parties involved. Okay, so with Ethereum, the security, it's a public blockchain. The smart contract executes publicly on the blockchain. Everybody can view the smart contract address and the actions taken. Anyone using etherscan.io can witness the execution of the contract. Whereas with Hyperledger, which is a permission contract, smart contracts are deployed by peers within either an organization or amongst different organizations. The access control is very clearly specified during the deployment. Only peers in the channel can invoke the smart contracts and view the transactions. With consensus, since end users can be trusted with validating logic, proof of work, or similar consensus mechanisms are required. Consensus is defined in the endorsement policy. Since users are trusted, selective endorsement is actually sufficient. With respect to scalability, this is very low due to a large number of nodes and proof of work consensus. However, recent developments like sharding, etc., are being developed to scale transactions on the public network. Relatively higher for Hyperledger, it's relatively higher. The scalability is higher because you have only a few nodes, and these are basically selected into companies or firms who actually control the execution environment. However, large scale deployment, similar to the popular Ethereum based applications, have not been developed on Ethereum and have not been developed with respect to Hyperledger, and because it's a permission blockchain. What are the different applications of blockchains? Okay, so firstly, and smart contracts, initial coin offers and decentralized application ICOs. So we have seen a whole huge spurt in ICOs. These are smart contracts that operate on permissionless networks as well as and offer several interesting business implications and considerations for both information systems and economics students. Okay, so initial coin offers are emerging alternate mechanism for raising capital, often leading to a much faster capital acquisition route. However, since this is not regulated, there is a scope of a lot of scams as well in this sector, because of which the United States has virtually banned all ICOs except those registered with the SEC for private coin or token offers. To better understand ICOs, explain how smart contract architecture and the business logic implications of this method of funding exist. So ICOs comprise of two initial design steps: issuing digital tokens and specifying the transfer parameters for these digital tokens. So in particular with Ethereum, the ERC20 standard, Ethereum request for comment 20 standard, is a standard software specification for actually issuing new tokens. And when the creator specifies the token name, the symbol, the total supply, the price in terms of the Bitcoin or ETH, the fundraising period, amongst others, and exactly why, how, and why are these funds raised, and how and why are they going to be used at the end of the day. So once these ICOs are disclosed, then retail users can go and invest either in Bitcoin or Ethereum and purchase tokens by those firms issuing those ICOs. Okay. Why would you need ICOs? So there are different governance models, which is like how are tokens issued, how are these tokens capitalized by entrepreneurs, and various decision making rules for businesses. So innovations such as DICOs, wherein all the users who actually own the tokens issued by a certain company can vote on different business model proposals, etc., and can get proportional voting rights. They can influence the disbursement of capital and future business directions of the firm, right? So these models need tokens to be dispersed. And then there are equity issuance models. Like for example, you could just issue shares of a company in the form of a token. You don't have voting rights, or you don't have shares, and then you can do is subject the user who holds this token to certain rules for holding, selling, and divesting these tokens. So equity issuance policies are similar to monetary policies of central banks, and this governs the mechanisms by which equity is issued. Eventually, it is said that many different countries in the world are actually considering releasing their own national currencies as cryptocurrencies, which is a possibility, right? And then you have revenue models. The underlying business model and mechanism by which the firm is issuing the token eventually ends up earning revenues, right? So all firms are set up with a purpose of returning value to the shareholders or increasing value to the shareholders by employing people productively, right? So once these profits are realized, then the end users can actually can get a share of this. Uh, Similarly, you have rewards and recognition models, wherein participants in the network are rewarded commensurate to their participation on the network. And I have studied certain business models like Steemit uh, and Cosmos Network, EOS, etc., wherein user-generated content creators, like for example, if you blog, you earn cryptocurrencies. If you basically participate by voting or moderating content, you earn cryptocurrency, so on and so forth. So you can basically reward people in terms of crypto tokens for just participating on the network. So these are the reasons why tokens are generally issued. Um, So another application is that of a B protocol. B verify is a protocol uh, for issuing and transacting in verifiable records using a public blockchain. Like, for example, if you want to get somebody's birth record, or if you want to get somebody's credit report, or if you want to get somebody's house ownership record, or the record of of a car's ownership, then what happens is you basically use a B-Verify protocol to get it, because it's all stored on the blockchain in exchange for a small fee. Okay, so MakerDAO is another recent innovation. It's mostly used in decentralized finance. So here, what happens is people who own Ethereum or Bitcoin or other currencies like BAT, it supports three of them, I guess, today. You can deposit it into a contract, a decentralized contract, and in exchange of your deposit, you can actually retrieve what is known as DAI. DAI are these tokens for which are pegged at $1 per token. So this DAI holds a stability because Ethereum is locked into the contract using a system known as a collateralized debt position, or CDP. And usually the CDP to DAI issuance ratio is uh, 1 is to 3. Like, for example, if you deposit $300, you can withdraw about $200 worth of DAI. And then this DAI, since it's pegged to a dollar, you can use this $200 for anything that you want. Like, for example, you want to buy a house, you want to buy a car, you want to pay for something, so on and so forth, without selling your Ethereum. You can use this, and once you get the money, once you can repay the money back into the contract, then your original ETH is released back to you. You can use it for other investments, so on and so forth. So, however, this collateralization ratio is over collateralized. Like, for example, to reduce the risk, right? Um, and users who actually participate on this platform through the CDP route have the way to make use of their capital without actually selling the crypto tokens that they hold. Okay, it's almost like going to a bank and withdrawing and taking a loan on your fixed deposit without actually divesting a fixed deposit or your recurring deposit um, therein. Okay. So another large area that is actually being impacted is that of security tokens. So the security tokens are used to create very unique financial instruments that you have never seen so far, or you might not have heard so far. Like, for example, uh, different types of financial instruments for, like, say, cross-border or cross-national arbitrage can actually be created using these smart contracts. Similarly, with decentralized finance applications, retail owners of stable coins, cryptocurrencies whose values are fixed, can engage in peer-to-peer lending, like, for example, in compounded finance or the Celsius network, or use other smart contract-based financial applications, bypassing banks, networks, and national state boundaries, and you can actually earn interests that are pretty attractive. So, for example, Celsius network promises about 8% interest rates for deposits in stable coins, right? So, but how secure is it? Is it backed by the government? You don't know, right? Like, so tomorrow, if the company shuts down, you may not be FDIC insured, and you could lose all your crypto deposits there. There is that risk, however, but with smart contracts, you can assume that such risk is mitigated because it's transparent. It runs on top of the blockchain, so on and so forth, and you can really monitor how the firm is operating or how the smart contracts are actually using the money that is locked up. Okay. Similarly, real estate owners could securitize their rental properties and trade them in open markets as dividend earning properties and sell such security tokens to interested parties. So, like, for example, if you own large amounts of assets, right, like, for example, real estate, instead of renting it out to some Airbnb traveler or somebody there, you could basically put it up on the market and basically borrow against the property from the most attractive rates, right? And that is, you could basically issue security tokens. You can divest 25% of the equity in your house and give it out on the market without paying a transaction fee and raise capital for, say, reusing in some other business. Okay, so both the ownership, dividend transfers, and value shared are automated using smart contracts, thus reducing the risks of defaults and other issues which actually happen with regular contracts. There are many artificial intelligence applications also on the blockchain. Like, for example, the automation of business functions at a very high level of trust lends itself to advancements in areas such as automated reasoning in artificial intelligence. So this is a very cool and recent application of this application. So what is automated reasoning or rule-based verification or formal verification? It is that branch of software development which has been plagued by several inadequacies because you have different levels of automation test suites and dependencies on human labor, etc. Like for example, if you're validating or doing the testing of a particular software, what are the rules against which you will test? You know, how will you test against certain rules? So these are very difficult to actually engage in. Whereas with the blockchain, it is assumed that once the rules are set, you set it up as smart contracts, incentivize say testers, incentivize testing software, etc. This formal logic can become validated through consensus mechanisms, like say a majority of the network will approve that this test case passes all the conditions needed for passing, right? For example, firms such as Synthetic Minds, which formally verify the logic behind programs, enable automatic generation of contracts from existing code bases, and they simulate the behaviors of contracting parties with generated contracts. Then there are other concepts as well, like EVASM, Everledger, IBM Food Trust. So IBM Food Trust is a solution as a service cloud platform built on Hyperledger Fabric. It is considered as one of the few enterprise blockchain systems that have been fully deployed at scale. In addition, the IBM Food Trust tries to build an ecosystem for all players that touch the food supply, including not just the retailers and suppliers, but also other third parties. For example, auditors who ensure process compliance and service providers who track temperatures throughout the food transport process. Smart contracts were implemented, provide services in three different modules. The tracing module facilitates the tracking of food products throughout the ecosystem. The certification module verifies the provenance of products that have been digitally certified as organic or fair trade. And data entry and access module provides participants the ability to upload, manage, and access their data within the system. There are different challenges with smart contracts. For example, software vulnerabilities, the legalities, and the disputes of adjudication. What if the smart contract fails? Whom would you blame? Who should pay the penalties, etc. There are different challenges in transforming business process and smart contract applications as well. However, Kumar et al. Have this paper in which they say that the wordings of rules and policies specified in the plain text can be rather convoluted and they do not lend themselves easily to mapping into executable programming language constructs and for use by smart contracts. So let's consider the simple clause in flight delay insurance policies, right? So this is actual wordings. When the terms and conditions are met, a party is eligible for reimbursement of reasonable additional expenses incurred when a purchase trip is delayed for more than 6 hours or requires an overnight stay. Now, who decides what the terms and conditions are? Are these terms and conditions fixed, written somewhere in stone? Not necessarily. The company can always argue that the terms and conditions are not met. There are different challenges with smart contracts, right? Like this class, right? Desired ambiguities such as reasonable expense leave the parties and flexibilities to work out a resolution when an unanticipated expense occurs. So such a clause can hardly be represented formally or measured objectively, since a programming language contract code needs exact specifications like what are the terms and conditions, like say if it's delayed, what are the reasons by which it's delayed, what are the acceptable reasons why it's delayed. And firms, both the insurance company and the customer, will hesitate to sign something that is so specific, right? That's why they leave it open ended. Secondly, executing contracts often requires information from third parties. For example, the insurance policy does not cover delay due to public hazard, which may be known to the party prior to the party's departure. Right? An independent authority may be needed to validate that such a hazard is actually plausible and legally acceptable. Third, however, to ensure that a smart contract determinism, a state where every party has to reach the same conclusion after execution, a smart contract is unable to retrieve off chain resources but can request a trusted third party called an oracle to push the necessary resources onto the blockchain system. The dependency on oracles for off chain data raises risks of erroneous data and weakens the benefits of decentralization. Increasing the reliability of such systems has been subject of recent research and has included recommendations to crowdsource information building and creating reputation models, and providing fault-tolerant subsystems that are variant of other blockchains at the end of the day. So blockchains and smart contracts, though they are intertwined closely, are not devoid of problems and faults, right? So there are lots of these weaknesses in smart contracts that are subject to research, and over a period of time, all of these problems will go away. So having said that, I would conclude this lecture on smart contracts.